Okay, so in terms of defining velocities and change of position, that's this. You learned this last year. Velocity is displacement divided by time. Okay, and displacement is change in position. So on your Science 10 formula sheet, it actually looked like this. Final position minus initial position divided by time. All of those things are the same. Okay, velocity is the rate of change of position. Displacement is change in position. Time is time. Okay, change in position divided by time, or the rate at which we change our position. Okay, that's the vector part of it. Right? You also had this formula. Which was different. Speed, which is scalar, is distance, which is scalar, divided by time. Okay? We're talking about, if we're using both of these formulas, we could be talking about the same trip, just from different points of view. Okay? And point of view in physics, as in life, is very important. Okay? I could be talking about how far I had to walk to get to some place that was actually really close to me. Okay? Which means my distance might be very large, because I had to walk around a whole bunch of things to get there, versus it was really in a straight line only this far from me. So when I get there, my displacement is this really small number with a direction, but my distance is this really big number because I had to walk all over the place to get there. Okay? It's the same trip, but it's from two different points of view. Right? So those two stories might sound a lot different. Okay? Like Darth Vader betrayed and murdered your father. Darth Vader is your father. Okay? Well, it's the same story, but it's two very different points of view. Okay? Context is important. One of these things is scalar, one of them is vector. Okay? So we need to make sure that we're keeping that in mind. Okay? All right with that so far? Okay. Now, there's something we need to realize about how we do things in mostly North American society, but also in other places in the world. And that is that we talk about how far away things are completely wrong. Okay? So, for example, if I ask you how far it is to Edmonton, how many of you are thinking of a number in hours? Because that's how we think. If I ask you how far it is to Edmonton, am I asking you how long it takes or how far it is? In physics, I'm asking you how far it is. Okay? We're trained to tell people when they ask, hey, how far to your house? It's 10 minutes from here. That's wrong. That's how long it takes you to go there. Can that change? Absolutely. Okay? If my wife drives to Sobeys from our house, it takes her 7 minutes. She has far better light karma than I do. That same trip will take me 12 or 13 minutes because I hit every damn red light on the way there. Okay? We travel the same distance. Okay? Sobeys is just as far for her as it is for me. We're on two different sides of the garage. Okay? The distance is exactly the same, but the time is different. Okay, guys, like I've driven to Edmonton countless times. And it is anywhere from 3 hours to 9 hours from here. It all depends on what the roads are like, what the traffic is like. But guess what? Edmonton is always, at least along Highway 2, about 365 kilometers from here. Okay? That's not going to change unless the continental plate in North America splits open between here and there. Okay? Center to center is going to be that distance. That won't change. That's how far it is to Edmonton. Okay? So we have to get our mind around that a little bit because we've been trained that far means long, and that it doesn't in physics. Okay, so if a question says, how far is it from A to B, you have to tell me it's this many meters, or kilometers, whichever would be appropriate, not how many minutes or hours it would be. Okay, so we just have to be mindful of that. Because, I mean, in a real world situation even, that can be misleading, borderline even dangerous. Okay, I'll give you an example here. An old teaching buddy and I used to go backpacking in the summertime. He's a physics teacher as well. And we were doing this one day where it was over 2 passes, like a 38-kilometer day. And we'd been hiking all day. It was 5 o'clock. We got an early start. We were out of water. We hadn't come across a creek to filter water from, so we were thirsty, hungry, tired, and we thought we might be lost because we thought we should be at the campground already. So we sat down and looked at the map and we're like, no, are we here? Are we there? Like, we gotta be close. That or we took a wrong turn somewhere and we're wildly lost. So we're sitting there, we're talking about it, and all of a sudden we see this guy, and he's like jogging / running uphill. In hindsight, wearing army fatigues and carrying a really heavy looking 70-pound or so pack, running uphill towards us. And we're like, oh, let's ask this guy. Maybe he came from the campground. So we're like, hey, dude, stop for a second. Comes over, in hindsight, not hardly breathing heavy. Okay? And did you come from Tumbling Creek Campground? He's like, oh yeah, Mike, it's down the trail there, about 20 minutes, be there in no time. I'm like, sweet, all right, 20 minutes, we can have water, we can make dinner, we can not be hangry and stupid anymore, we'll be good. An hour later, we stumble into this campground. And I mean stumble, I mean, you know how it gets when you get dehydrated, headache, the whole works, it was bad. In fact, about halfway there, we were like, okay, maybe we should turn around. Maybe that guy was an idiot. Like, we're not there yet. He said 20 minutes. It's been like 40, and we're not there. What's going on? So we get there finally. We've cleaned some water, had something to drink, had some stuff to eat, plotting how we're going to catch this guy and tune him in for screwing us over with his 20-minute lie. And then we got to thinking, and I looked at my buddy, and I'm like, hey, Sean, you know what we just did, right? Yeah. And we will never speak of it again. Which, of course, I'm breaking down because I tell the story every semester. But we allowed somebody to tell us a distance as a time. This guy was probably Australian Special Forces out for a run with a heavy pack. He was running with a 70-pound pack. We're two out-of-shape teachers going downhill, and it took us 60 minutes. Okay? Now, if he'd have told us the campground was 4 kilometers away, we would have known that would have taken us an hour. We weren't running. We were stumbling. Okay? He was running. So it can be a situation like that. If you tell somebody that Edmonton's 4 hours from here and in the middle of a snowstorm, 4 hours later they're not even in Red Deer yet, well, maybe they don't know their way. Maybe they think they've really screwed up and they're really lost. Okay? You got to give actual distances when someone says how far. Okay? At least in physics, that's really important. Okay? Everyone all right with that? Okay, so we do have to kind of change our thinking a little bit in physics. All right, now let's say I'm describing a trip here. Let's say I'm telling somebody how far it is from Okotoks to the Calgary Zoo. Okay, so I'm going to start here in Okotoks and I'm going to drive probably along the Deerfoot here and then go in on Memorial and go into the zoo. Okay, and I tell somebody, yeah, it's 40 kilometers. Okay, is that okay? Are there lots of signs on the road? They probably get to the zoo if I tell them the zoo's 40 kilometers from here. You don't get more detail than that on the road signs, do you? Right? You're driving along the highway, it says Strathmore, 20 kilometers, or it says Lethbridge, 150 kilometers. It doesn't say which way to go. It assumes you're going to follow the road you're on, because it's a safe assumption. Okay? In that situation, a scalar description is appropriate. Okay? If you're already on a road that's going south, the sign doesn't need to say it's 150 kilometers south. You're just going to follow the road. Maybe you get to an intersection and it'll say Lethbridge, turn right. Well, then you will. Okay? You're still going to go 40 kilometers to get there, or 150, whatever I said it was. Okay? That's okay. Scalar descriptions in that situation are appropriate. Okay? If I said to the person, it's 40 kilometers, 13 degrees west of north, that might be true, but unless they're getting there by helicopter, that's probably not the best way for me to describe how to get to the zoo. Would you agree? Right? It might be interesting, but it's not really useful. Okay? Not in that situation. Now, what if you're the navigator on a cruise ship? Is a vector description going to be better for you if you're out on the ocean? If I want to go from New York to Barcelona, I better know that it's this many kilometers on a heading of this, because I'm going to travel in a straight line across the ocean, as long as there's no islands in the way. Pretty sure that route would not involve crossing any islands. Okay? If you're an airline pilot, Same thing. Okay, you got to use vectors. You point your plane on a certain heading and you go that way. Okay, you're not going to follow the roads unless you're on that flight from Calgary to Edmonton, then you kind of fly over the highway. But okay, most of the time you're going to need vector descriptions for that. So in some situations it's appropriate, in others it's not. Here's a weird question for you. Which of these is more accurate? Talking about how to get to the zoo. Which one of those is more accurate?
The first one?
Actually, it's a trick question. I'm sorry. I played a trick on you. They're equally accurate. See, we get this idea that if I put a vector on it, I'm adding accuracy. Accuracy comes from measurement. How did you measure that? Okay, so if I tell someone something is 40 kilometers from here, that actually means it's somewhere between 39 and 41, right? The last thing I measured was this value. So this is accurate to plus or minus 1 kilometer. So is this one. Okay, I measured these the same way. Now if I suddenly did this, now which one's more accurate? First one. Okay, first one's more accurate now because this one is accurate to plus or minus 100 meters. When I say it's 40.8 kilometers, I mean it's somewhere between 40.7 and 40.9. That's way more than plus or minus 1 kilometer. Accuracy depends on how did you measure the magnitude, not whether or not you put a vector on it. Okay? Putting a vector on it adds description, but it doesn't make it more accurate. But we get that impression. There's more there. It must be more accurate. Not necessarily. Okay? I could have a vector. I could have said this instead. I could have just said 4 times 10 to the 1. Okay? Now it's only accurate to plus or minus 10 kilometers. That's not very good. Okay? But it's got a vector on it. That must mean it's, no. It's just because it has a vector on it doesn't make it more accurate. It just gives you different information. Okay? Everybody all right with that? That comes up. Someone's like, well, vector's better. No, not always. Some situations it is, some situations it isn't. And it's definitely not always more accurate. Okay. So a more descriptive description is to give the vector. That does have more descriptive stuff in it. It has that additional set of values, okay, of the 13 degrees west of north. Okay. Everybody all right with that idea? So that's where the trigonometry is going to come in. We're not there yet, but we will be by next week. We'll be talking about this many degrees east of north or west of south or whatever, and we'll start drawing triangles and have trigonometry come in. Okay, you guys are still familiar with vectors in the negative, positive way from Science 10. Okay, so let's look at this whole scalar versus vector point of view thing. Okay, so let's say I'm doing this. I have got to walk from my house to Walmart. Okay, now there's really nowhere in town where you can walk from a house in a straight line to Walmart. Okay, there's usually a fence or other houses or obstacles that you can't walk through in the way. Okay, you can't really walk directly to Walmart. So if I want to walk to Walmart, okay, let's say I'm going to follow this black line because I'm walking. Okay, I have obstacles to worry about. Okay, so I'm going to follow the black line and I'm going to go a little ways west. Okay, I'm going to cross the river. I'm going to go this way. Obviously, this is not in Okotoks because there's not a river south of Walmart here. Okay, but I'm going to go this way, and eventually I'm going to end up at Walmart. All right. Well, let's say that I have my step counter on, and when I get there, it tells me that I have traveled a distance of 4 kilometers. Okay, is that how far Walmart is from my house? Walmart's a lot closer than that, but I can't go that way. Okay? I have to travel 4 kilometers distance in order to get there. Okay? Even though when I get there, my displacement, that is my change in position between my house and Walmart, will be a smaller number because displacement is always the straight line. Right? And as we all know from like grade 4 geometry, a straight line is the shortest route between 2 points. Okay? All right, so when I get to Walmart, if I, like put on, like a, map program or something, I'm like, oh, okay, well, it's actually only this far. Let's say that if I was to walk along that line, that my displacement would be 2.8 kilometers at 38 degrees north of west. Okay? That's how much I've changed my position. Okay? That's how far directly I am from my house. Unless I had a helicopter, I couldn't go that way. Okay? But that's how far I've changed my position by. Everyone following the difference? Okay? Same trip, but two different points of view. Both accurate. Okay? Both equally meaningful. Now, because I'm old and I forget things, I get all the way to Walmart after walking 4 kilometers. Okay? And I realize I've forgotten my wallet and my phone and I have no way to pay for anything. So I'm not going to walk around Walmart for the fun of it. So I'm going to go home. Okay? Now let's say it took me a half an hour to walk to Walmart. How fast did I walk? When I ask how fast, am I asking about speed or velocity? Anybody ever get a velocitying ticket? You don't generally get a velocitying ticket. You usually get a speeding ticket. Okay, I'm talking about speed in that case. How fast is how quickly you change distance, how quickly you add on distance. Okay, if I know that this formula is true, speed is distance over time, I take my distance, 4 kilometers, and I divide it by half an hour. Okay, divide anything by 0.5 and it's like multiplying it by 2, right? If I'd have walked for a whole hour, probably would have gone 8 kilometers, right? It'd be fair to say my speed's 8 kilometers per hour if I walk 4 kilometers in half an hour. Okay. What's my velocity? Velocity is displacement divided by time. Do I know my displacement? Yeah. It's on there, right? It's 2.8 kilometers at 38 degrees north of west. Okay, how long did that take me? Time's the same, right? Doesn't matter that I didn't actually travel this line, it still took me a half an hour to do it. Okay? Time's going to be the same whether I'm talking about the scalar part of this or the vector part of this. Remember, it's the same story from different points of view. So it still took me a half an hour to change my position by 2.8 kilometers, 38 degrees north of west. So the time is the same, which means my velocity vector quantity, it needs to have that direction on it, is 5.6 kilometers per hour at 38 degrees north of west. Why is it a smaller number? Did it take me just as long to not go as far? Right? I mean, we know the shortest route between 2 points, okay, is the straight line, right? So that straight line is not 4 kilometers. Okay, I walked 4 kilometers in a half an hour. I changed my position by 2.8 kilometers. Still took me half an hour to do that. Okay, so my velocity is going to be smaller. Okay, everyone all right with that? Now, is it okay that the vectors on these two are the same? Well, they sure better be. Okay, last time I checked, I can't travel 100 kilometers per hour north and end up east, right? My velocity and my displacement, they come from each other, so they have to be going the same direction. Okay? If I'm 2.8 kilometers, 38 degrees north of west, my velocity is also that way because that's how I got there. Okay, so those two are always going to have the same vector. All right, so back to the I'm old and forgetful part. I get there and I decide I'm not going in there, so I turn around and I walk exactly the same route home. It takes me another half an hour to get home. What's my total distance traveled? 8 kilometers. Yeah, okay. I walk the same route back. It's still 4 kilometers. Okay, so now I've walked 8 kilometers in total, and round trip, it took me an hour. So what's my speed? Is it still 8 kilometers per hour? Sure it is. I walked 8 kilometers in 1 hour. That's 8 kilometers per hour, for sure. Okay. What's my total displacement when I get home? 0. I may have walked 8 kilometers. From a scalar standpoint, it keeps adding on, right? The more I walk, the bigger that number gets. But displacement is your change in position. My initial position is home. So is my final position, which technically means I didn't go anywhere. Okay? I may have walked 8 kilometers, but because I ended up where I started, my displacement ends up being 0. So what does my average velocity for the whole trip also end up being? 0. Okay? Because velocity is displacement divided by time. If this is 0 and this is 1 hour, 0 divided by anything, still 0. Okay? I accomplished nothing from a vector perspective. Even though from a scalar perspective, I was walking for an hour and went 8 kilometers. Okay? Same trip, different points of view. So it's just important to realize that we can talk about something like that and have the numbers be wildly different. Okay? All right. Now, what if I drove this? Okay? I have my car instead. You get that little thing in your car. It's called an odometer. It tells you, measures your trip. Does it measure distance or displacement? Distance. Yeah, it's sure better. Okay? Because otherwise, what would it read every time you came home? 0. No, it would measure how far it is from the dealership you bought the car at to your house. It'll read 0 when you go get an oil change. Sorry, that was a jerk move, but it's true. Okay, we'll say yes. Okay, if home is your starting point, it would always read 0 when you came home. Okay, well, that's great if you're selling that car. You could have driven it around the world 3 times. As long as you bring it home, it's going to say it has no kilometers on it. Okay, and you could totally rip somebody off. Back in the day, you used to be able to actually wind them back, and some people did. And just say instead of having 1.5 million kilometers, and just click that back. Now it only has 500,000 kilometers on it. Okay, now it's all digital, so unless you can hack the computer, you're not going to be able to do that. Okay, so if that's something that has to measure distance, it has to be scalar. Otherwise, it can't do its job. Okay, you need to know how far that car has been driven if you're going to buy it. Okay, you don't want to buy something and go, oh, it says 0. Well, that's because it's parked here at home. How far did you really drive it? Okay, that's an important thing to know. So in some situations, again, distance is more appropriate, displacement's more appropriate here. Okay, all depends. Questions on that? Okay, you would have done stuff pretty similar to that in Science 10. Okay, so another example of which is going to be more appropriate, displacement or distance. So let's say I'm here at Chown Creek Campground, and I'm going to walk on this particular day from Chown Creek Campground all the way here to Snake Mountain Campground. Okay, right here outside of Chown Creek Campground is a sign, and it says Snake Mountain or Snake Indian Mountain Campground is 39 kilometers. What is it giving me? Distance. What is it assuming I'm going to do? Follow the trail. Yeah. Okay. It's going to mean, okay, it's 39 kilometers if you do this. Okay? Because that's the logical way to go from A to B. Okay? That sign is not going to say, okay, that Snake Indian Mountain Campground is 19 kilometers at 40 degrees south of east. If I'm flying a rescue helicopter, that would be useful. Okay? If I'm walking, that is death. Okay? Because if I walk on the trail, everywhere where there's a river, there's a bridge. Okay? Safe. Walk across. It's easy. Okay? If I walk this way, I've got to ford rivers, bushwhack through forests, and cross glaciers. All these gray things are glaciers. Okay? Glacier travel is dangerous. There could be a crevasse and you could fall in it. Okay? I don't want to go that way. In this case, a scalar description, distance, follow the trail dummy, is the way to go. Okay? And that's what we generally use for that type of situation. But again, like a navigator on a boat, an airline pilot, any kind of pilot, you're going to use vectors all the time because that's going to be the best way to get from A to B. Okay? Okay, so as we were talking about distance and displacement, one's scalar, one's vector, but they measure how far. Okay, speed and velocity, one's vector, one's scalar. They measure how fast in what direction. Okay, important to know the difference. Okay, I mentioned the velocity ticket and the speeding ticket earlier. Like, okay, you get pulled over by the police and they come up and ask you, how fast were you going? They want to know your speed. Okay, if you tell them I was going 126 kilometers per hour, 13 degrees south of west, there will be follow-up questions, usually involving you trying to walk a straight line and do like sobriety tests, because that's not the thing they wanted. And it's a really weird way to answer that question. Okay, 130 kilometers per hour, I'm really sorry, officer, it's the better way to answer that question. Okay, or not to speed at all and not get asked the question in the first place would even be better. Okay, but if you tell them your velocity, yeah, that's going to be weird. That's going to set off some alarm bells. Okay, so one measures the right thing, one measures something else. Okay, what's time? Is time scalar or vector? It's scalar. In our experience, time only goes forward. Okay, we sometimes in North America use it like a vector. Where do you live? I'm 10 minutes east of here. Oh, so now time is vector? 10 minutes east? No, it's not. Okay, it'll take you 10 minutes to drive there if you go east. Okay, those are two separate things. Okay, time is scalar, it only goes forward. If you ever get a negative value for time, you either did something wrong, that's the more likely situation, or invented a way to travel backwards in time. Okay, because if you get a negative time, you went into the past somehow. Okay, we're always traveling into the future. So you're all time travelers. You're just traveling at the same speed as time. It's just somewhat boring, but okay. All right. So we talked about this, how when you go home, okay, your distance is always getting bigger. Distance doesn't have direction. It's scalar. It's always adding on. But displacement can go up and down. It depends on which way you go. Okay. All right. So this is just a quick review here. Scalar quantities are any measured quantity that only has a value. 40 kilometers, 75 kilograms, 2 weeks, okay? All of those are scalar quantities, okay? Distance, scalar quantity that measures how far the object has traveled, keeps adding on. Speed, scalar quantity that measures how far an object travels in a set time interval, 10 meters per second, 100 kilometers per hour, okay? It's the rate at which you increase your distance, okay? Vector quantities, any measured quantity that has both value or magnitude and direction, 40 kilometers forward, 3.2 kilometers, 18 degrees west of south, 700 newtons down, 9.81 meters per second squared down. Acceleration and force are both vector quantities. Okay, energy is a scalar quantity, like 200 joules, that would be scalar. Okay, but yeah, we're going to deal with kind of which things are scalar, which things are vector. Okay. So displacement, vector quantity that measures how far and in what direction an object has traveled from its starting position. That starting position part is important. It's change in position. Okay? Vector quantity is basically the rate velocity, is the rate at which you change your position. That's still going to be in meters per second, usually for this course, or kilometers per hour. Okay? And then you got your formulas here. You don't need to write those down. I'm going to copy some new formula sheets for you. I just didn't get around to it. I was going to give you the old ones, and then I realized just how much crap was written on them, so I'll give you guys some fresh ones probably tomorrow. Okay, but these are the formulas, obviously, we used today. Okay, and we'll be using those tomorrow as well. Okay, I want you guys to write this question down, and we're going to go through it here. This isn't in your notes package anywhere. We're doing problem-solving practice questions. Those you'll have to write down. They're not in the worksheet booklet, and they're not in the notes package. These are ones we'll have to go through together. So I'll give you a few minutes to write that one down. This problem here is one of your basic displacement, change in position kind of questions. All right, so initially, the person is standing 1.5 meters to the right of this inukshuk. Okay, so that is their initial position, because that's where they start. Okay? Then they move to the left. And at the end of this question, they're standing at a final position that is 3.5 meters to the left of the inertia. Okay? So the question wants us to solve for their total displacement. Right now, we can kind of do that almost commonsensically. We can just kind of look at that picture and go, okay, they went 1.5, then they went 3.5, they went 5 meters to the left. Okay, we can kind of see that in the question, right? They went 1.5, then they went 3.5, that's 5 to the left. Okay, the question also says using algebra, right? Find the displacement algebraically using plus and minus signs. Well, if these are vector quantities, one of these has to be negative and one of them has to be positive. Generally, we make right positive. So we can say displacement is final position minus initial position. Okay? If left is going to be negative, so I usually do this, negative, okay? Negative 3.5 minus 1.5, okay, meters. Well, negative 3.5 minus 1.5 comes out to negative 5.0 meters. If negative is left, that means they went 5 meters to the left. Okay. Would I get that wrong if I left it as negative 5 meters? I would. The question didn't give me positive and negative. The question used the words left and right. Therefore, my answer has to refer back to those original directions. We're going to do that a ton with vector addition. We're always going to be converting a direction to positive and negative. East and west, we're going to have one negative, one positive. Okay? We're always going to be doing that. Then at the end, we have to come back and go, all right, it's west, or it's northwest, or it's whatever. Okay? All right, we'll leave it there for today, guys. We'll pick up where we left off tomorrow.